the person who derived all the properties in the factorization here. Okay? Double sheets, enriched double sheets. 4 is for number of 0 and pi. So to D4, meaning that you have a minimum phase, D4. Because 0 inside the big circle. So when I say minimum phase, is that I'm looking at all systems have the same order, order 7, have same magnitude response. This one has the smallest phase lag. Okay, that's what it means. It means that among all systems, the FIR system with 7 zeros. Okay, 4 here, and the 3 here. I have the same magnitude response. So I'm allowing to flip this in and out. Right? This one has smallest phase lag. That's what it means. You can show it. You can show that it's a long proof. You can show that if I flip the 0 outside, the phase will increase. Again, using all paths properties. Again, linear phase solution is important because you want in image and video, phase alignment is very important. An edge, right? If you have out phase, you see ghosting artifact. So when you want to use transformation, that is linear phase. That's why all the wavelets using compression are linear phase. The DCT, the discrete cosine transform using JPEG, is also linear phase, and so on and so forth. Okay? So now the phase is very important for image and video, because you can see if it's the out phase, you can see the ghosting artifact. So here, linear phase solution. Again, F naught, H naught. Okay? Now, many different solutions. We'll discuss a few. Okay. So how do I deal with this pair? They go together. So how about the other? I want linear phase and let's say real coefficient. Okay. Both linear phase and real coefficient. How do I deal with this? This set of 4 zeros. Do they have to go together or not? Together. Right? If you want linear phase, then this pair go together. If you want real coefficient, then this pair go together. If you want both, all 4 have to go together. Okay? Let's give it to the other side. Otherwise, it will be not fair, right? So that's one way to distribute 0 that's not like -1. Okay? And here you can put 4 and 4. Alright, that's one way. This is called the 9-7 wavelet. 9 or the 8 zeros, 9, length 9, right? Or the 6, length 7. This is the 9-7, this is used in JPEG 2000. This is the best in terms of compression, the best wavelet to use in terms of how good it is, and also how, in terms of implementation also. Of course, you go into a higher order system, you have higher signal to noise ratio, but the complexity might be too big. So this is a good trade-off between length and complexity, okay? And also PSNR. Another choice is I can have 2 here, the other set there. I can have 3 and 5. Right? And so on. So you see that the other choices basically is how I distribute the 0 at pi. right? And so on. 97 is a length. Right. There are 8 zeros. 8 zeros order 8, and you have a constant length 9. Okay? So in this particular factorization, the only one that you need for linear space, you need to remember it's a 97J vector factorization. Okay? And there are many ways to factorize this. And have both linear space and real coefficient. But basically, you have to distribute the zero part. So let me pause for question. And any question regarding different ways to factorize, how do I factorize, and so on. Is that clear? Okay. Let's talk about half band filters. Design. Okay, I need help. How do I start? Yep.
I think you should start with one linear phase on orthogonal filter.
So you want to narrow down the scope of the design. That's good. So let's design linear phase, half band filter with real coefficient. Good. How do we start that? How do I? Yeah, that's symmetric. How do I find it? How do I characterize a half band filter? How do I know that it's a half band filter?
This have only one.
You can look at the impulse response, right? It's 1, and then every 2 points go to 0. That's one way to do it. Okay, so you can say that, okay, what do I know about half band filter? I know that there's a center of symmetry, L. Right? L's R is 1, and I don't really care what this is, but an L minus 2 and L plus 2, the one exactly 0. Right? The next point, I don't care what this is, and then an L minus 4, L plus 4, and so on. That's one way to do it. But that's hard to do, right? I have to figure out how to choose this coefficient. How do we design our filters? Forget about half band. How do I design low pass filter? This is low pass half band, right? How would you design low pass filters? Using MATLAB. What does a low pass filter look like, right? You want to find somehow, this is omega. You want to say in a range from 0 to omega p, which is the pass band, I want it to be approximately 1. Right? And I want omega s, 2 pi, approximately 0. I want a method to somewhat, approximate or find its coefficient. And then when I plot it, plotting p naught of e to the 3 omega, I have an approximation. Right? I have something like this, and then like that, right? With magnitude, so like that. Okay? So there are many ways to design this, right? Riemann or empirical is one way to do it. What you have to do is you have to figure out what is the length, what is omega p, omega s, what's the weighting between the deviation